Hello students, welcome to your physics class. So today we are going to start a very important module for you. It is the module on oscillations. So you must have encountered oscillations in various spheres of life. In everyday life, you must have encountered oscillations. And on the slide, what you see is an example of oscillatory motion, the oscillation of a spring mass system. So you must have encountered this kind of oscillatory motion very frequently. So we are going to learn about such various kind of oscillatory motions. But before that, let us look into a more generalized picture. Let us look into what do we mean by periodic motions. So, as we all know, periodic motion is a motion which repeats itself after regular interval of time. So periodic motion gets repeated after regular interval of time. And here I have put forward for you various examples of periodic motion. One such periodic motion is the motion of our Earth around the Sun. The revolution of the Earth around the Sun is an example of periodic motion. And the period of motion, or the period after which the motion gets repeated, which is also known as the time period of motion, that is 365 into 1 plus 1/4 days. 365 and 1/4 days, as we all know. The next periodic motion that I have brought for you is the motion of the Earth about its own axis, or rotation of the Earth. The motion of the Earth about its own axis, or rotation of the Earth. And the period of this motion is, as you know, 24 days. Sorry, what I mean is 24 hours. And the next kind of periodic motion that I have for you is the motion of a simple pendulum. So this motion also you must have encountered a lot, the motion of a simple pendulum. And the pendulum, as you see, moves from its central position, position 1, to one of the amplitude positions, position 2. Then it moves back to position 1 and then moves forward to another amplitude position, position 3. And this is how it continues its to and fro oscillatory motion. So this is a simple pendulum. Okay. So let's proceed. Now that we have understood what is periodic motion, we would look into a special kind of periodic motion, which is oscillations. So oscillation is a periodic motion in which a particle moves to and fro along the same path. So in oscillatory motion, your particle is moving to and fro along the same path. So every oscillatory motion is a periodic motion, but every periodic motion is not an oscillatory motion, because in every periodic motion, the particle in motion is not moving to and fro along the same path. Now, various features associated with oscillatory motion. First is the time period, which as I have mentioned already, is the time required to complete one oscillatory motion, or the time after which the oscillatory motion repeats itself. And as we know that in SI units, the unit of time period is seconds. Next is frequency. Frequency of oscillatory motion is the number of oscillations per unit time. So its unit is second inverse or hertz. The next term associated with oscillatory motion is equilibrium position. So equilibrium position is a very special position along the path of the oscillatory particle. It is that position where the particle experiences no net force. Okay, so if we look into this picture of simple harmonic motion, here position 1 is the equilibrium position. The position 1 is our equilibrium position. Why? Because no net force acts on this oscillatory particle at this position. And why does no net force act on the particle at position 1? That is because the weight of the bob, the oscillating bob acting downwards, which is mg, that is completely balanced by the tension T in the spring, in the suspension wire for simple pendulum. So mg is equal to T tension in the suspension string at equilibrium position. So no net force is acting on the bob at position 1, which is why this position is a very special position known as the equilibrium position. So let's proceed. Next is displacement. What do we mean by displacement of an oscillating particle? The displacement of an oscillating particle is its distance from the equilibrium position. Is its distance from the equilibrium position. So again, going back to the example of our pendulum, when it is at position 1, its displacement is 0 because it is sitting at the equilibrium position. And when the oscillating particle moves to the one of the extreme positions known as the amplitude position, then its displacement is maximum. Then again displacement reduces, becomes 0 once the particle reaches the equilibrium position. Then again it increases and becomes maximum when it reaches the other extreme position or the other amplitude. And this continues. And amplitude, as I said, it is the maximum displacement encountered by the oscillating particle when it is at one of its extreme positions. Next, we would move into a very special kind of oscillatory motion, which is known as simple harmonic motion. So simple harmonic motion is a special kind of oscillatory motion. Why is it special? It's special because in simple harmonic motion, the force acting on the oscillatory particle is always directed towards the equilibrium position. The force that is operating on the oscillating particle at every position of its path is directed towards the equilibrium position. So the force tries to bring back the oscillating particle to its equilibrium position. And the force is directly proportional to the displacement of the particle. At every position of its path, the force acting on this particle, this force that is directed towards equilibrium position, that is known as the restoring force, because it tries to restore the position of the particle to its equilibrium position. That restoring force is directly proportional to the displacement of the particle or its distance from the equilibrium position. So that's it for today. We will continue with our discussion in the next class. Thank you for your attention.